There we go. It's 3 o'clock. We have 3 people here out of 12. We're going to get started. So here's your exam from last time. If you want to solve for this, I said, remember, you have b to the x, where b is a number like 2 to the x, or e to the x, or e to the anything up there, whether there's a variable up there, all right? These are always positive, okay? Any exponential function is positive. Remember, the graph of an exponential function looks like this. It goes through 1, because anything to the 0 power is 1. So that's 0, 1. All right. So you see that they never cross this line. They're never equal to 0. They're always positive. So if you want to solve something like this, and you notice this showing up, you want to do, pull that e to the x out. All right. So looking at this, since this is always positive, the only way this whole thing is 0 is if this is 0. Okay, because this is always positive. And this just tells you x squared equals, let's see, 8 divided by 4 is 2. So x has to be a positive or a negative 2. Okay, the e to the x actually doesn't affect that at all because it is never 0. This guy is never 0. E to the x is never 0. It's always positive. Exclusively positive. Notice I did not put equals. It's always bigger than 0. So we do the same trick with the second one here. We can pull out the e to the minus x. We get an x squared minus 9. And even though that's negative, so what? E to the x, I said, looks like that. If it's a negative exponent, that just looks like it's exponential decay. But still, it's always greater than 0. Okay? E to the x is always positive. Should do this over here. Make it like green. Make that a little better. E to the x is always positive. E to the negative x is always positive. All right. Here is y equals 0. They're always above that line. Okay. So if you're solving when is this equal to 0, since this is never 0, this whole thing can only be 0 if this is 0. If you move your 9 over and take the square root, you can see x would have to be a positive or a negative 3. And there's your solutions. All right. All you have to remember is that the exponentials can never equal 0. Okay. You plug a big number in for x, you get a big number. If you plug a negative number in for x, you're going to get a 1 over e, which is just a really small number. Okay. Okay, so now we need a quiz, but before we do our quiz, I want to do a quick recap of what we talked about last time, which was exponentials and logs. Okay, so here's like a chart here. This is from the log section. This is from section 2.6. 2.5 is exponential. So here's an example of 2 to the x. It looks like this. All right, like I said, the exponential never crosses that line. This is 2 to the x. 3 to the x would look like that. 4 to the x would look like this. 10 to the x would look like this. They all look the same. It's just the bigger the base, the faster it grows. Okay. And over here on the negative side, let's say you have a -1 here. 2 to the -1 is just a half. It's 1 over 2. 2 to the -2 would be 1 over 2 squared, or 1/4. So that's why when you go this way, your exponential function just gets smaller and smaller. It just gets closer and closer to 0 there. And if now logs, okay, Logs are the inverses of exponentials. So remember this line y equals x, when you go from a function to its inverse, right? Remember, if f of x equals y, then f inverse of y equals x. The inverse function is just a function that does the same thing but backwards. So you can see the x's and y's are getting switched. So graphically, what that means is you're flipping over the line y equals x. So if this is 2 to the x, this red line is log base 2 of x. Log base 2 of x is the inverse of 2 to the x. So you could say two things here. Log base 2 of 2 to the x is x. They undo one another. Or you could say 2 to the power of log base 2 of x is x. That's what you're doing when you're putting one function inside of the other. I'm saying f inverse of f of x is just x. Whatever f did, f inverse undoes it. Whatever this 2 to the did, the log base 2 undid it. If you do log base 2 and then 2 to that power, they undo one another, all right? So that's why the graphs of logs look like the graphs of exponentials, but flipped over the line y equals x, okay? So exponentials are always up here, right? Exponentials are always positive. All right, and since the domains and ranges get switched, you can see by looking at the log here, the log is not over here. There's nothing over here. You cannot plug in a negative number into a log because the numbers that come out of exponentials are always positive, okay? Think about it this way. 2 to the x, all right? I can plug any real number I want in for the x, and the output is always going to be positive, okay? So how can I write that? B to the x, right, maps the real numbers to the positives, right? So here's what b to the x looks like. Look, the domain, it goes infinitely far left and right, doesn't it? Right, the graph goes infinitely left, infinitely to the right. That's why you can plug any number in, but your output is always positive, okay? Then your logs look like this. So I'll do this one in red. The log base b of x, all right, since it undoes what the exponentials do, whatever came out of an exponential, that's what can go into the log. Its job is to undo whatever this thing did. And so whatever comes out is what goes in, and whatever went in is what should come out, okay? So if you look at the graph here, the output of log, right, you can plug in positive numbers, and what comes out is your y values here. Every up to 0 and then down to negative infinity. So this would be negative infinity up to 0. So the logs are always giving you negative numbers. The log is not up here. The log is down here, right? Y is negative down here. Okay, so the logs always spit out a negative number. So you cannot plug in a negative number into a log. So this saying a to the x equals y, or I'll call it b. B to the x equals y is the same thing as saying x equals log base b of y, okay? So think about this as a function. You plug in x in, it's an exponential, and you get an output. To say the same thing as a log, this statement is exactly the same as this statement. And you can see that because if I take log base b of both sides of this thing, the log base b and the b to the undo one another because they're inverses. And that's what I wrote over here. So that's why that this is the same as that. You can write something that's exponential form, you can rewrite it in log form. So what we're looking at is x is the log, the x is the exponent. So logarithmic functions are inverses of exponential functions. But a log by itself, just the log, not as a function, a log is an exponent. You can see the log here is x. X is the exponent. So if I write something like this, log base 2 of 8, and I ask you, what is that? This is an exponent. This is the exponent you have to raise 2 to in order to get 8. So a way to do this, you could rewrite the 8 as a 2 cubed. Then the log base 2 and the 2 to the undo one another, and you get a 3. So like log base 5 of 25. No, it's not. Yeah. Well, this is asking 5 to what power is 25? Well, you can write the 25 as 5 squared. And then the log base 5 and 5 to the undo one another, and you just get 2. This is 2 because 5 to the second power gives you 25. All right. If I did this another way, 2 to the log base 2 of 7. What would this be? Well, 2 to the log base 2 undo one another, and you just get your 7. Okay, because they're inverses. Just like if I put the exponential inside the log, if I put the log as an exponent, all right, that's how you undo one another. So for a quiz here to deal with logs, here's your try that again. Daily quiz number 21. Let's simplify. So if I have log base 2 of 16, I'll do log base 3 of 27. Do log base 4 of 64. Log base 6 of 36. Log base 8 of 64. Log base 9 of 81. Put some over here. 7. 2 to the log base 2 of 6. 3 to the log base 3 of 3. 6. I'm just gonna throw some regular exponents. So 6 to the no, I don't want to do that. Now I'll do that with the exam later. All right, here we go. I already did it. 5 to the log base 2 of 4. This one, you have to figure out what that is first, okay? So 6 to the log base 3 of 9. 2 to the log base 3 of 81. And number 12. 4 the log base 2 of 4. Okay, so these are exponents over here. All right, it's really important that you notice that 2 to the log base 2 of 6, this is not the same thing as 2 times log base 2 of 6. When you're writing your math, you need to be write very clearly. You can't just, write chicken scratch everywhere, just, roughly. So if you're like copying somebody else's work, you're definitely going to write things totally incorrectly because you're not interpreting it. You have to be very careful, right? This guy is in the exponent. That's okay, Mandy. All right, so just remember to recap here. 2 log base 2 of 8 is the 8 is the same as 2 cubed. Log base 2 and 2 to the undo one another. So you just get the 3, right? It used to be an exponent, it's not anymore. All right. something like this, log base 2, I'm sorry, 2 to the log base 2, these are inverses. So if this thing is in the exponent, those undo one another and you just get your 7. Something down here, like this guy, you could just do this, right? Because the bases are the same. This one you cannot do that because this is a different base, right? But you can evaluate this first, right? Because 4 is 2 squared. So you could figure out what that number is and then raise 5 to that power, okay? And your calculators will do this for you, right? But you want to be able to look at this after we're done with these solutions, you should be able to do these in your head, okay? Because these are not that hard. Once you understand it, it's just pattern recognition, okay? And it's hard because you never really seen it before, but once you just practice it a little bit, you'll see that's pretty easy. These logs are really counterintuitive, so we want to get the basic math manipulation down so we can, because they're going to show up a whole lot in business and finance, just constantly. Okay, let's take 10 minutes at 3:26. We will work these together. All right, so let me squish these a little bit over here. So 16 is 2 to the 4th, right? 2 times 2 is 4, times 2 is 8, times 2 is 16. Yeah, 16 is 2 to the 4th, and log base 2 and 2 to the undo one another, and the 4 comes down out of the exponent. 27 is 3 cubed, and log base 3 and 3 to the undo one another, you get 3. 64 is 4, 4 times 4 is 16 times 4. So 64 is 4 cubed, those undo one another, and you get 3. 36 is 6 squared, log base 6 and 6 to the undo one another. 64 is 8 squared, so those undo one another, and you get 2. 81 is 9 squared, those undo one another, and you get 2. Let's take these, put them on the next page. We have some room. Oops, I stole something here. Over the P, that's okay. All right, this guy, 2 to the log base 2 undo one another, and you get 6. 3 to the log base 3 undo one another, you get 3. This one you can't do that because this is a 5 and that's a 2. What I can do is try to figure out what that is. 4 is 2 squared. So the log base 2 and the 2 to the undo one another, and you just get that 2. And 5 squared is 25. Okay. Here we can't undo those because they're not the same base. But I can rewrite this 9 as 3 squared. And 3, log base 3 and 3 to the undo one another. So that 2 comes down, and 6 squared is 36. Same issue here. We can rewrite the 81. 81 is 9 times 9, and 9 is 3 squared. So this would be a 3 to the 4th. Log base 3 of 3 to the undo one another. 2 to the 4th is 16. Here, there's a couple of ways we could actually do this. You can't just do that because they're not the same base, right? But I could take this 4 here and rewrite it as 2 squared, and then the log base 2, and the 2 to the undo one another, and I still have this 2 here, and 4 squared is 16. Or I could have rewritten this as 2, the 4 is 2 squared, right? Let's see if there's something we could do here. So this is an exponent. So what we have here is an exponent to an exponent, right? This would be a 2. That wouldn't help. So you can't do that because this is here, okay? Just can't do that. We're going to learn later a nice trick though. We're going to learn that if you have a number times log of something, you can bring that number in and put it as an exponent. All right. That's going to be a trick that we're going to learn in this section. So we could take that and put it in there. We could be like, we could take this 2 and put it in an exponent of the 4. We could do that. And at this point, you could say the 2 to the log base 2 undo one another. You just get the stuff on the inside. It should be 16. Okay. We're going to use this. All right, but we haven't introduced it yet. We'll need that a lot. So remember I said, if a to the x equals y, I keep using a, I like a, we'll use b. This is the same thing as saying x equals log base b of y. So logarithmic functions are the inverses of exponential functions, right? That's why 2b to the log base b of x is x, or log base b of b to the x is x. This is saying exponential functions and logarithmic functions are inverses of one another. But this statement is the same as this. Again, if I take log base b of both sides, those undo one another, and I get x equals log base b of y. Right? These are the same. So even though logarithmic functions are inverses of exponential functions, x here is the exponent, and the exponent is the log. So logs are exponents, is what they are. Right? That's why you could say log base 2 of 8 is 3, because 3 is the exponent you have to raise 2 to in order to get 8. This log is the exponent you raise this to. So logs being exponents, they satisfy the same properties that exponents do. An exponent to an exponent, you multiply them, right? If I have an a to the b to the c, this is a to the b times c, right? So that is why, all right? That is why if I have r times log of whatever m, this is an exponent, this is an exponent, we're multiplying them, right? Okay, we're multiplying exponents. That's the same thing as having an exponent to an exponent. So that's why this thing can be written, you bring this and put it in there as an exponent. So this, an exponent to an exponent, you multiply them. That's why you can do this, right? An exponent to an exponent, you multiply them. That's how it plays out, okay? And we also have this fact, a to the b times a to the c is a to the b plus c, right? If you have a like base, you can add the exponents when you're multiplying. That's why log of m times n is going to be log of m plus log of n. All right. All right. It's like having a like base. This is reminiscent of that. It's the same feature. These logs are exponents, but that's how the notation plays out. Or if you're dividing, if you had a to the b over a to the c, right? This is a to the b minus c. If you have a log of m over n, that's going to be a log of m minus log of n. And the reason why is this guy could be written like this, m times n to the minus 1. So this is log of m plus log of n to the minus 1. And this guy says, you have an exponent here, you can bring it out front, right? And since it's just a minus sign, you're getting this. So this guy is just this, where you have an n to the minus 1. So that minus 1 comes out. And that's why it becomes negative dividing. So that's what this, I think this next section is going to be about. That's what my guesses are here. Let's see, here's some examples. Let's do these. So A, This is equal to, let's see, we have log base 5. 25 is 5 squared. So those undo one another and you get 2, right? This guy, B here, you have log base 9. If you can write 3 as 9 to some power, 3 is the square root of 9. Right, those undo one another and you get a half. This guy here, if we can write 1/4 as 2 to something power, because we're looking for what exponent you raise 2 to in order to get 1/4. You would have to do a 2 to the minus 2, right? The minus puts it on the bottom, right? 2 to the minus 2 is 1/2 squared, 1/4. So those undo one another and you get the minus 2. Okay. Questions about this? It's the same thing over and over again. Okay, so far. We'll ease into those new rules that I showed you. You're going to see why we're going to need them with our finding interest, solving for interest and stuff like that. Here's more of the same stuff. So log base 3, 9 is 3 squared. So those undo one another. You just get 2. This guy, log base 4. The 2 here we're going to have to write as 4 to the 1/2. So those undo one another and you get a half. C here, we'd have to write the 1/9 as what, a 3 to the minus 2, right? This would be 1/3 squared or 1/9. Then those undo one another and you get a minus 2. So as long as we can make these things work out, using the fact that they're inverses of one another, these are easy, right? But it's there's not very many problems where you can actually do this. Usually this is different than that, and then it just sucks, right? And you have to figure out another way around it, okay? See, half of y'all turned in your exams last time. I'll remind you, there is a tutoring lab right down the hall, right? So every day after class, you could just go straight there and in 10 minutes have your test done every day and make straight hundreds on all your tests. All right. I'm not allowed to beat y'all, so all I can do is tell you over and over again, and sometimes make fun of you, because it's easy to do your work, do your job. All right. You're making it look like I'm not doing mine. And last night I had this nightmare. A colleague of mine invited me to go on vacation in Afghanistan. For some reason in my dream, I thought, okay, cool. And there's like Taliban and war everywhere. And I had my 2-year-old daughter with me. And it was like, this dream went on for like 45 minutes. And then I realized I forgot to take my nicotine patch off before I went to bed. Like, oh. You can, but you're going to have wildly vivid dreams. Usually they're good dreams, but in my pre-cal class, I had one of my Afghan vets went ballistic when the Wi-Fi went out in the classroom during our online exam. Yeah, just lost. It was cool. So I think that's why I was stressed out all day. There's nothing I could do about the Wi-Fi going out. It's worked every day, every class for the last year that I've been teaching there. It's the only time that's ever happened. All right, let's look at this one. Change each exponential form to an equivalent logarithmic form. Not sure what they want us to do here. So how would we rewrite that? 64 equals 4 cubed. They want us to write it like this. So our base here is 4. So I would be like, they want log base 4. That's how I'm going to go. I'd be like, okay, the base is 4. And then I would be like, okay, 64 is 3. That's what they want. Yeah, that's what they want. Why is that equivalent? Because let me try that again. Log base 4. 64 is 4 cubed, right? This is log base 4 of 4 cubed is equal to 3. So they want you to write it like this, though. All right, this is a true statement. 64 is 4 cubed. This is a true statement because 3 is the exponent you raise 4 to in order to get 64. My brain doesn't work this way because I wasn't raised with logs. Anybody that was born like, like a decade before me, they're going to know logs inside and out because logs were their version of a calculator. They did not have calculators. They had a book that was full of logarithmic tables. So if you multiplied big numbers, again, logs are exponents. So they use the fact that they use these exponents. You add the exponents instead of multiplying big numbers. You rewrite these big numbers. Like 64, you rewrite it like that, and 128, you would rewrite it like that. And instead of dealing with these being multiplied, you're basically adding these, right? So 64 times 128, that's 4 cubed times 4 to the 4th, which is 4 to the 7th. So instead of multiplying these, you would add these, and then you'd look it up in the table to see what 4 to the 7th is. Something like that. I'm not sure how they used it, but it was real fast if you knew your logs and your exponentials, right? Log was their shorthand for a calculator, right? So what it does is it turns multiplication into addition, all right? So adding's easy, right? Multiplying big numbers is hard, especially if they're really big numbers. So it allowed them to multiply big numbers really fast. They just had to look it up in this book to see what their answer was going to be. It's faster than using an abacus, or a slide rule. I have a collection of those. I don't know how to use one, but I should probably learn just for the fun of it. It just doesn't seem that fun to me. So if I look at this, part B here, I see that 36 is my base, right? This is 36 to the 1/2. So since that's the base, I'm thinking they want something with 36 as a base. So they're saying log base 36 of 6 is a half? No. What do they want? Yeah. Because 36 to the 1/2 power is equal to 6. Okay. So part C here, to write this in that logarithmic form, first I look at the base. They have a base 2 here. Now I got to figure out where the other numbers go. Log base 2 of 1/8 is equal to -3, because 2 to the -3 is equal to 1/8. Okay. I guess if you practice this, this becomes just as natural as this, but I haven't had to do that a lot. So I always think about things in exponential form. All right. So I spend most of my time taking this and rewriting it like that so I can wrap my mind around it. But we want to be able to do it both ways. It's counterintuitive. Look at another one. Change each exponential form to an equivalent logarithmic form. So A, since 7 is the base, I'm going to start off with log base 7. And then I'm going to put a 49 equals 2, because 7 squared is equal to 49. Here, my base is 9, so I'm going to write down log base 9. Log base 9 of 3 is 1/2, right? This is 9 to the 1/2. So we're saying 9 to the 1/2 power equals 3. Over here, my base is 3, so I'm going to write down log base 3. And I'll say log base 3 of 1/3 equals -1, because 3 to the -1 is equal to 1/3. All right. The only thing that's allowing me to do this is focusing on the base. That's the one thing I know. That's the base, so it goes there. From there, I figure out there's only 2 other numbers. I have to figure out where they go, right? And I just think about it. This to that power is equal to that. And let's read their little paragraph. Maybe it'll help. To gain a deeper understanding of logarithmic functions and their relationship to exponential functions, we consider a few problems where we want to find x, b, or y in this equation. So there's 3 numbers. There's a y, a b, and an x. We want to be able to isolate any one of those. Right now, the y is isolated, but what if we want to get the b by itself or the x by itself? Okay. All values are chosen You do not need a calculator. Okay, so if you're using a calculator, you're doing it wrong. Anyhow, I have a blank page in my notes. Example 3. Let's look at A here. Solve for y. Well, y is already by itself. All we have to do is evaluate this. 16 is 4 squared, so y is equal to 2. So we didn't have to do any manipulation here. B here is a little harder. We have log base 2 of x equals -3. How do we get the x? How do we get the x out of the log? So this log is doing something to the x. How do we undo what log does? Well, what's the inverse of log? It's exponential. So since it's a log base 2, I'm going to do 2 to the power of both sides. All right, so these things both become exponents. That way I could say those undo one another. And now I have x is 2 to the -3, which would be 1/8. So to get the x by itself, you have to make that go away. Raising 2 to that power is what undoes it. Right? The log is an exponent. So, and it's where it's supposed to be. So that's why they undo one another. Let's see, let's look at C here. Here we have log base B of 100 equals 2. It might take a little while. So how do we get this B here? What I could do is, just like the last problems we did, we took these we took exponentials and we rewrote them as logs. You can write the logs as exponentials. My brain always breaks down. What I would do here is I would do b to the power of both sides. I want to get rid of this log, that's for sure. So if I do b to the power of both sides, that log goes away, but I'm trying to solve for b. I still have a b over here. You see what I mean? So those undo one another. I have 100 equals b squared. Does that make sense? I mean, this is the one that's going to break you. You're going to be like, how do I get that b? You just get rid of it by doing b to the both sides. But over here you have this b squared. Well, if b squared is 100, the b has to be either a positive or a negative 10. All right, so this is the crazy one. So y'all can handle it now. Now you know how to do it. Let's do some more of these. Look at A. A is easy. The y is already by itself. All we have to do is evaluate. 27 is 9. No, this is harder, right? We can't write 27 as a power of 9, can we? It's kind of hard. It is a power of 3, and 9 is a power of 3, right? Well, I guess we could do this. We have to write 27 as a power of 9. 27 is 3 cubed, right? So that would be a 9 to the 3 halves, right? So we have the square root of 9 is 3. So we would have to rewrite 27 as 9 to the 3 halves power, okay? It's the square root of 9 cubed, right? So this one's kind of tricky because you look at it and you're like, it's not an integer power, it's a fractional power, right? The connection is 27 is a power of 3, but you need it as a power of 9. So you get your 3 here as saying it's the square root of 9. But 27 is 3 cubed. If you cube both sides, all right, that's the trick. So now those undo one another and you're getting 3 halves. All right, I'll follow that trick there. Kind of tricky, but it's not too bad. Just getting you have to get used to these fractional exponents now, and it's almost always over 2, you know. Okay, to get this x, how can we get to that x here? If I look at this, I got to get rid of this log. The inverse of a log is exponential. So I do 3 to the log base 3 equals 3 to the minus 1. So I'm doing a base 3 on both sides so that that will go away. And then I have x equals 3 to the minus 1, which is 1/3. This one, the b is in the exponent, in the base again. So what I'm going to do is I'm going to do base b as an exponential of both sides. So I'm going to do b to the power of both sides, so that goes away. And then I can solve for my b. That's what we're going to do. So I'm getting 1,000 equals b cubed. 1,000 is 10 cubed. So therefore, b has to be 10. And you could plug it in. Once you get your number, plug it in over here. B is 10. 10 to the third power is 1,000. So you can check your work, right? Just like you always, whenever you solve for x, plug it into the equation to check your work. We found b was 10. You replace b with a 10. Yes, 10 cubed is 1,000. So we did all this math to figure this out, right? But technically, you should be able to look at this and write down the answer. Something cubed is 1,000. Well, the answer has to be 10, right? So even though this was the craziest one, because the b was in the base, the math was kind of weird. If you understand it, you should be able to just write down the answer. Something cubed is 1,000. What's the something? It has to be 10. 10 cubed is 1,000. Okay. So here's where they talk about the tricks I showed you earlier. Properties of logarithmic functions. The tricks that are going to help us out here. All right, here's the proof where if you have log, and I hate that they don't put parentheses. There should be parentheses here, okay? We write f of x, right? It's a function of x, f of x. Log is a function, right? It's log of something. We never write fx because that's a crappy channel on cable TV, right? But if you're lazy like them, they just leave out the parentheses, and that sucks. Those parentheses really should be there, okay? It gives you the false impression that log by itself is a thing. It's the name of a function, okay? So if you just have like log and then like a three times log, if you write something down like that, that doesn't make any sense at all. Log of what? You have to include the argument. So here's their proof here. Let's see. To show that log base b of m times n is log base b of m plus n, to show that you can separate it, you can replace this multiplication by addition, you have to rewrite m and n in exponential form. So if you let m be b to the x and n be b to the y, you just replace them. And then you have b to the x plus y, and then these undo one another. You get x plus y. Well, x is log base b of m, and y is log base b of n. You don't need to understand the proof so much, but you are going to want to be able to use it. So there's the proof. So that's one property. Some of these I've already told you over and over and over and over again. Okay. Log base b of 1 is 0. This is because anything to the 0 power is 1. Okay. This b is the same thing as b to the first power. Those undo one another and you get 1. Okay. So log base b of b is going to be 1. Those undo one another and you get your x. These undo one another and you get your x because they're inverses of one another. All right. Here we just showed that if you're multiplying, you could turn that into addition. This is new. And the one below it is just the same thing, but if you're dividing, you have to subtract, okay? And here's the other trick I showed you. If you have an exponent in here, you can pull it out front in front of the log, okay? And if you have log base m, log base b, as long as the bases are the same, then m and n have to be equal. It's like saying if I have 2 to the x equals 2 to the y, x has to equal y, right? The two to this are the same z's on both sides. The log base m, the log base b is on both sides of the whole thing, so you just get rid of those. And the way you can see that is do b to the power of both sides, right? The b to the log base b undo one another. So that's how you would see that clearly, okay? So this one, those two are new, and we're going to use those a lot. I didn't see a proof of it though. Oh, okay. Simplify. Okay. For part A here, we could do, when they say simplify, they really should be saying expand. Because I think this is simple. What they want us to do here is write, this is equal to log of W plus log of X minus log of Y minus log of Z, right? These are multiplying, so you add. These are divided, so they have to be subtracted. This is not simple. This is simple. So their instructions to me are just like, that's the opposite of simple. They should say expand. I think that's what they want, is they want you to expand it. They want you to take one object and turn it into 4 objects. So let's look at this one. This is terrible notation. Are they raising this to the 3/5? Or is the 3/5, see, is the 3/5 inside of there, or is it out here? I don't know. Those are two totally different things. Okay. I think what they mean is this, okay? Because they do this half-ass crap where they don't put their parentheses, and that's total bullshit, right? This is not log base b times m times n. This is a function of mn, but because I see that they just leave out parentheses, I'm assuming that they need parentheses here, okay? So log of wx to the 3/5, this is not the same thing as log of wx to the 3/5. And if you don't put parentheses there, you don't know which one it is, okay? It's like saying f of x squared, that's not the same thing as f of x squared, right? Totally not the same thing. So I know they want it this way because they want us to use our little trick. Because like this, we can't use that trick they just showed us. So this is the same thing as log base b of, we can bring the exponent out. That's what they're saying here. You can bring out the 3/5. And then you have wx, right? So you have 3/5. Since these are multiplied, you could turn it into addition. Okay, so we're using two properties here. The one where you can move the exponent out front, and the other one where you can turn the log of a product into sum of logs. Let's look at part C here. All right, this guy, it's hard to see, but this is log base E here, okay? Log base E, they should be writing as ln. Remember, ln is shortcut for log base E. All right, y'all remember that? Natural log, there's a button for it. Okay, so they want to, what we have to do here is this x is in the way. So let's go e to the x log base E of B, okay? What we can do is bring this x and put it in here. as a exponent. Okay. Remember, an exponent you could put out front. If you have something out front, you could put it in as an exponent. So now the e to the log base e undo one another, and you just get a b to the x. Okay. And now d. This, they want you to make the mistake. This is not log base e of x minus b. All right. Remember, log base e of x over b, that would be log base e of x minus log base e of b, right? If they're divided on the inside, you can turn it into two logs. So that's the rule. There's no rule for this. So you can't do that, okay? That's not what this rule is saying, right? Multiplication on the inside says you can subtract them on the outside, right? So what you can do though is, what can we do here? Log base e of x over log base e of b. No. Dividing logs. Okay, I could write this. No, it wouldn't work. Of x. This is a change of base formula. We have log base e of b to the minus 1. I don't know what they want us to do. Let's look at their answer on part B. Yeah, it's the change of base formula is what they're wanting us to just come out with. We're deriving the change of base formula. So check this out. This requires some intuition here. This is equal to that. This is your change of base formula. If you have a log base b, but you want log base e, you can change the base for your log by doing this backwards, okay? So if we're looking at this and we want to condense this into one log, we can because these are the same base. So what we do is rewrite the x. X is b to the log base b of x, right? Those undo one another, right? So we're going to use that to rewrite this. We rewrite the x as a b to the log base b of x. Now, this is an exponent, which means we can bring it out front. So that's why we have the log base b of x times the log base e of b. And that's the same thing that's on the bottom. So those cancel out and you just get the log base b of x. This is the change of base formula. I can never remember it. But that's the trick. Anytime you have like, here's the number 7, and I want to write it as a log, right? I could be like, this is log base, I could write it as, pick a number 3 to the log base 3 of 7. I can always do that, right? Those undo one another, and it's 7. So you cannot, and I could do it with any letter I wanted, any number I want. B to the log base b of 7. Right, those undo one another and you get 7. That's a trick that we use a lot. Okay. So when we're looking at this, the fact that these are the same, I know that I can rewrite this x as a b to the log base b of x because those undo one another, right? It's just x. That's the trick right here. This is that. Then you can take the top part, the exponent, pull it out front, and then it'll simplify. That one's hard. That is the change of base formula, though. That's something they're going to put in a box, put a red rectangle around it. Because the thing is your calculator only has a log base 10 and a log base e, right? So if you need to use your calculator to evaluate something and it's a log base 4, your calculator doesn't have a log base 4 button unless you paid extra. So you're going to have to use this formula here, your change of base formula, in order to change it to either base e or base 10. So log base b of x is natural log, or whatever log you want, log base whatever you want. I always use natural log over natural log of b. This is your change of base formula. Whatever number you have here, if it's not something your calculator can handle, you can change it to log base e. You just change it, and then you have to do the natural log of your old base on the bottom. You have to divide that out. Change of base. Sounds like a bad 80s rap band, right? Change of base. Let's take like a 5 and 6 minute break. All right, break time, break it down. Resume at, I don't know, do like 4:15. We'll take a 9-minute break here. Recording. Log an exponential. Match problem 4. Okay. A. This is log base B of R. Since these are being divided on the inside, we can subtract them. Log base B of S, a log base B of T. This one, they really mean this. So we could take this exponent and put it out front. 2/3. And we have the R on the top and the S is on the bottom, so we can subtract. These are log base B. All right. You always want to put your base. If you just write log without a base, that usually means log base 10. All right, your calculator might have a log on it without a base. If they have that, they mean log base 10. Usually, unless you're in like Europe or something. All right, this one here, we can't do this because this u is in the way. But we can do that we could take this u and put it in here as an exponent. This is log base 2. We could bring that u in as an exponent. Now the 2 to the log base 2 undo one another, and we have a b to the u. D. You can't do anything here, but what we can do is we can replace this x, replace the x with a 2 to the log base 2 of x. See, those undo one another. This is just x. That's what that is. We're just rewriting x like that. Okay? And then we have a log base 2 of b. Now, why did we do this? We don't want to do that. We just put this there on purpose. We can do this, though. Or, since this is an exponent, we can bring it out front. Right? If we did this, we would just have what we started off with. If we did this, we'd still have log base 2 of x. Right? Doing that or doing this is going to give you what we started off with. So you don't want to do either one of those. This is an exponent, so we can bring it out front. This is log base 2 of x, and then log base 2 of just 2, right? If you move this out front, the only thing left in there is a 2. And now, what did I do now? B, yeah. No, I screwed something up. Log base 2 of b, log base 2 of x. X is, oh, we don't want to do a 2 here. We need to do a b. This is still just x, okay? Right, I got stuck. There's nothing I could do once we did that. Right, you want to do a log base b, because now if you bring this out front, then you just have log base 2 of b, and that's the same thing that's on the bottom. And then those cancel out. So you have a log base b of x. That's the simplifying. You can rewrite this like that. That's your change of base formula. So the goal ultimately is solve for x, right? You want to be able to solve, think about this. The amount is e to the RT, right? In order to solve for the interest rate or the time, right, if you know these others, you need to be able to get into the exponents. In order to get to the exponents, you're going to need logs. So this is really important for business. So you look at all this and you're trying to find out what x is. Usually you like to multiply. Like if we have like x squared plus 4x plus 4, this sucks. We like to rewrite that as a product. We take a sum and we rewrite it as a product, and then it helps us solve the equation. Here we have a sum, but we can rewrite it as a product. This you can bring in as an exponent. We have 4 to the 3 halves. This we can bring in as an exponent. Log base b of 8 to the negative 2/3. And then we have a log base b of 2. Why did I get rid of these numbers? I put them in as exponents because now we have a log plus a log plus a log without any numbers out front. So if you have the same base, remember this becomes, you could just multiply these together now. You have this times this times this, all in just one log. Okay, so I turned these 3 logs into a single log. I didn't do anything over here because that's where my x is. At this point, this is critical. This is all log base b, this is log base b. So if I have log of left-hand side equals log of right-hand side, left-hand side has to equal right-hand side, okay? To show this, what I could do is b to the power of both sides. So now I just have x is equal to this stuff, which is all numbers. So from here, we just need to simplify. The square root of 4 is 2, and 2 cubed is 8. The cube root of 8 is 2. 2 to the minus 2, the fourth. And we have this times 2 here. So we have 16 divided by 4 is 4, right? Y'all should be able to do this now. Let's look at this. I mean, first part was getting the x by itself. We used the properties of logs. We got rid of the numbers out front, put them as exponents. That way we have a log plus a log plus a log without numbers up front. That allowed us to turn it into a single log where these are all just multiplied together. If you have a log of stuff equals log of stuff and the bases are the same, you could just throw away the logs by doing b to the power of both sides. So that means that x is this stuff. So this is like last section stuff. How would we simplify this? These are all powers of 2. I showed you one way to do it in my head, right? I could rewrite 4 as 2 squared. 8 is 2 cubed. 2 is 2 to the first. An exponent to an exponent, you multiply. 3 times a negative 2/3 would be a negative 2. If we have like bases, we add them. So we have 3, 4. 4 minus 2 is 2. 2 squared is 4. That's one way you could do it. Okay. Let's solve another one here. You want to be careful. When you look at this, remember, I told you you cannot plug negative numbers into log. So if you do your manipulation and you get x equals a negative number, that can't be a solution. All right, some of these manipulations we do are actually adding extraneous solutions. So you have to get your answer and then look back and see, is that something I could actually plug into the log? Okay, we'll see that here in a little bit. So here, our left-hand side, we have these threes and these halves. That prevents us from combining these. But here you could bring the 3 in as an exponent. Here you can bring the half in as an exponent. This minus, you could bring it in as a -1 if you wanted to. Or you don't have to. If you want to keep it as a minus, you could do this a little differently. All right, so our left-hand side, since these are all log base b, log base b, log base b, we can turn them into 1 log base b. Since these are added, they become multiplied. Since this one was subtracted, it goes on the bottom. You could do it that way if you wanted. Now, since everything is inside logs, if I do b to the power of both sides, the logs can just be thrown away. So I have x is equal to this pile of numbers, and all we need to do is simplify. Okay. 2 cubed is 8. The square root of 25 is 5. 40 divided by 20 is 2. And you can check your answer. You plug in a 2 there and make sure that both sides of the equation are equal. Notice b went away, right? These two problems, right? There was 2 variables here. There's a b and an x. This equation is the same thing as saying x equals 2. The b here actually was irrelevant. Okay? Like saying x plus 1 equals x plus 1. This is true for any x. You get rid of the x's don't matter. I mean, yeah. Let's look at another one. All right, how do I get x? We have to solve for x, but x is showing up in 2 different places. So we need to combine these. There are no x's over here. At least all the x's are on one side of the equation. Okay. This guy, since there's no numbers out front, we can combine these. Log base 10. Since we're adding, this is going to be x times an x plus 1, right? If you're adding the logs, you can combine them, but you have to multiply the arguments. And the other side stays the same for now. At this point, since it's a single log and a single log, we can do 10 to the power of both sides, and those go away. So I get an x times an x plus 1 equals 6. And you know how to solve this by now. This is just a quadratic. All right, this is x squared plus x minus 6 equals 0. All right, multiply that out, get the 6 involved so you can set it equal to 0, and now you got a factor. We could do what a plus 3 and a minus 2. So x has to be a minus 3 or a 2. But you have to be careful. You cannot plug a minus 3 into this equation. This is not a solution. It's an extraneous solution. These little tricks we did actually added solutions. So remember how I would always do this? Like they're equivalent, right? These are not equivalent. At some point along the way, we added a solution. So from here, we only have a backwards implication, okay? This implies that, okay? Because if you plug a minus 3, this thing is undefined. This equation, you cannot plug minus 3 into it, so it can't be a solution to that equation, okay? If I plug a minus 3 in here, I would have a minus 3 times a minus 2. This would be positive. So you can plug a minus 3 into this one, okay? Well, really, we have this guy. Going from this step to this step, where we combine these logs, this new equation This one right here, this is not equivalent to that one. Because you cannot plug a -3 into this, but you can plug it into here. All right. So that's not a solution to the original equation. Okay. Again, because you can only plug positive numbers into logs. Remember, the graph of log looked like this. There's nothing over here in the negative world. There's no negative x's you can plug in. You can only plug in positive values. You always get back negative values. Okay. But the 2 is fine. You can plug the 2 in, it's fine. Like this guy, our solution, we got x is 2. It was totally fine. We could plug that in. But this guy has an extraneous solution. Notice, this is important. All right. When you combine logs, you might be adding extra solutions that are not solutions to the original equation. So you have to check. All right, we look at this. We could do the same trick. We have x's in 2 different spots. We got to get the x's together. We want to get rid of these logs. We can combine these logs. I could say log base 3. Since these are added, I can turn this into multiplication. This original equation, this x has to be positive, okay? Greater than or equal to 0. No, you can't get 0. Greater than 0. This tells you that x has to be bigger than 3, right? So overall, this is what matters, right? If I try to plug in a 2 into this equation, this is fine, but this one is undefined. So ultimately, this equation is only valid if x is bigger than 3, right? Because if you plug in something less than 3 in here, this is undefined. So this equation is only valid if x is bigger than 3. But notice, once I've combined these to make this equation, if I plug a 2 in here, let's see, I get a 2 times a -1, that would still be a problem, right? If I plug in a 3, I don't know, let's see. From here though, if I get rid of the logs, I could do 3 to the power of both sides. I could have x times an x minus 3 equals 10. I can plug any number I want into this, but this I can only plug in values bigger than 3. So these cannot be equivalent. This one has all the solutions this does, but it has more. So if we look at this, we could multiply this out, bring our 10 over, then we'd have to factor x minus 5, a positive 2. So x could be a 5 or a -2. You cannot plug a -2 in here or here, right? So that can't be a solution. 5 is the only one that's good here. Okay. So this equation implies this equation, but we do not have the other way around. We do not have an if and only if. They are not logically equivalent. They can't be. This has more solutions than this does. All right, let's read the long paragraph. Of all possible logarithmic bases, e and 10 are used almost exclusively. Before we can use logarithms in certain practical problems, we need to be able to approximate the logarithm of any positive number either to base 10 or base e, and conversely, if we are given the log of a number to base 10 or e, we need to be able to approximate it. Historically, tables were used for this purpose, but now calculators make computations faster and far more accurate. Common logarithms are log base 10. So when you see log base 10, that's the common logarithm. Log base 10. That's why they often just write log. If they don't say the base, really it could be any base, but it's assumed that you mean log base 10 if you don't write the base. Okay. Natural logarithms. Natural logarithms are ln. See, they say most calculators have a key labeled log or log and a key labeled ln, right? So if it just says log, they probably means base 10, and the ln means log base e, all right? But you have to be careful. Some places will use this as a log base e, which sucks. Another one that shows up in computer science is log base 2, which is often written LG because computers are base 2. Okay? Just be careful when you're using your calculator. Make sure you have the right base. All right, so here is a good example. Get used to your calculator. You're going to need it. So they tell you what the answers are. So this is log base 10. This is log base E. This is an LN, not an IN. Right? I've had students trying to put IN, capital IN into like Google to evaluate stuff, and they're like, IN isn't working. This is not an I, it's an L. LN. Okay. Log base E. This is the deal. This is undefined because you can't take the log of a negative number. Right? That's why it says error. That's why it's like, think about it, log base 2 of a -3. What power do you raise 2 to get a -3? There's no exponent you can raise 2 to in order to get a negative number. Okay. You practice the calculator, make sure you know how to use it. So how can we, what do we want to do? Solve, right? So to get the x here, since this really means log base 10, we would do 10 to the power of both sides. 10 to the log base 10 undo one another, and you have 10 to the -2.135. That you can type into your calculator. Over here, to get to the x, since this is log base e, we would have to do e to the power of both sides. And the e to the log, natural log, undo one another. And this you can plug into your calculator. So here, instead of using exponents to get rid of logs, we're going to use logs to get rid of exponents. This guy, we're going to take log base 10 of both sides. Those undo one another. So x is simply log base 10 of 2, and you can plug that in your calculator. Here, to get the e to the out of the way, we're going to take log base e of both sides, or natural log. Those undo one another, so x is simply natural log, and you can plug that in your calculator. This one, if we take log base 3 of both sides, check this out. These undo one another, and you get x equals log base 3 of 4, but you don't have a log base 3 button on your calculator, so what do? All right. Instead of using log base 3, like whatever that base was, turns out you can always use natural log. You can use any base you want because of the trick. So instead of doing log base 3, I'm going to take natural log of both sides. Now I can't do that because this is base e. What I can do is bring this out front. Bring it x times. Remember, as an exponent, you can bring it out front. So now that I got the x out of the exponent, I could just divide both sides by this number. This is going to be a log base 4 over a log base 3. Well, I got this answer a while ago, but now I got this answer. Those are equal. Remember your change of base formula? If I don't like that base, I could change it to any base I want. I just have to do the log of whatever that base is and divide by it. Those are equal, right? You can't plug that into most calculators. These you totally can. Okay, that's your change of base formula. Change of days. Mm-hmm. One more. All right, since this is a 10, I'm going to do log base 10 of both sides since I have a log base 10 button. Those undo one another, and x is log base 10 of 7. And that's a button on my calculator. Here, since it's e, I'm going to do natural log of both sides. Natural log and e2 undo one another, and I have a natural log button. I can plug that in. I do not have a log base 4 button. So instead of going log base 4, I'm just going to use natural log, or you could do log base 10. It doesn't matter. Just pick a log whose base you calculate it. The x will come out front. So now I can just divide by that guy. All right, and I have a natural log button, so I can evaluate this. Change those doubling times. So if you're investing money, the time it takes to double $10 is the same amount of time it takes to double $1,000. The doubling time is the same. It doesn't depend on how much you invested. If something's decaying, you talk about half-lives, okay? So if we look at our standard finance equation for compound interest, this is where it's always at right here, boom. What is the doubling time for an investment, all right? How long will it take the money to double if it's invested at 20%? R would be 0.2, compounded annually. That means M is 1. All right. So what we could do is, here's our thing. What we're looking for is, if we want our money to double, we want our amount to be twice our principal, right? So if we replace A with twice our principal, notice that in this equation, you can divide both sides by P. That's why the principal doesn't matter, okay? It doesn't matter what the principal is, it falls right out of the equation, all right? So now we're left with 2 equals this. All right, we have 2 equals 1 plus R over M. If we let M be, let's see, R is 0.2 and M is 1 times T. All right, just plugging those numbers in. 1 times T is just T. 0.2 divided by 1 is just 0.2. So we're looking at 2 equals 1.2 to the T power. How do we get the T? Okay, what we can do is natural log of both sides. Because now we can take the T and put it out front. T natural log 1.2. So the T here is going to be natural log of 2 over natural log of 1.2. Okay, that's the time it takes to double your money. Notice you have this 2 in there. That comes from the doubling of money. If you wanted to triple your principal, it would be log of 3. Or quadruple, whatever it is. So it pops up right there, because you're replacing the amount with a multitude of your principal. Okay, we could do this generically. All right, if we started off with this, and let's say I replace A with 2P, right? The P's go away. So to get the T by itself, if I did natural log of both sides, because this is an exponent, I can bring it out front. So I have a natural log of 2 equals MT, natural log 1 plus R over M. Okay, so the T here is this natural log of 2. I'll divide by m and divide by that. M natural log of 1 plus r over m. So that's the answer for, that's the doubling time. All right. How many times you're compounding your interest rate, right? So this problem, they actually gave you numbers, right? But we don't even need the numbers. We can solve this generically, all right? That's your doubling time. Doubling time. In fact, there's a 2 right there. You want to, let's look at time. You wanted triple time, that would be a 3. If you wanted 10 times your money, you put a 10. Okay. If you plug into your calculator, you get approximately 4 years. Let's look at another example. How long to the next whole year will it take money to triple if it's invested? So tripling means the amount is 3 times the principal. The interest rate is 0.13. Compounded annually means m equals 1. So our equation is A equals P times 1 plus R over M to the MT. That's our equation. Let's plug in what we know. Replace A with 3P. Replace R with 0.13. Replace M with 1. So if we simplify this, first thing you see is divide both sides by P. You have 3 equals, this is 1.13, and that's just T. So if I take the natural log of both sides, for the purpose of getting the T out of there, right? T, natural log of 1.13, and T is natural log of 3. It's going to divide by that over the natural log of 1.13. Again, we're having a 3 right here because it's a tripling time. Look at this little picture here. Logarithmic regression. So remember, the regression analysis is where you plug data into your calculator and it tries to come up with the function that fits it the best. Figure 6 shows the graph of this equation, doubling time in years for interest rates compounded annually from 1 to 70%. All right, so what they did was they used this generic, like this guy. All right, I solved it without plugging in M or R. All right, this is the doubling time. I could just graph this. I could fix M and graph it based on R. If I let M be 1, if M is 1, I would just get natural log of 2 over natural log of 1 plus R. So if I use this as a function of R and graph it, you get this graph right here. So this is the doubling time based on the interest rate. So how long would it take to double your money? Depending on what the interest rate is, right? If the interest rate is the same, it's always the same amount of time. But if the interest rate changes, you get this thing. This thing looks like, let's see, A plus B natural log of X. So this is a log, all right? Usually B would be negative because the logs are down here. If you multiply it by a minus, that puts it up here. And then you're shifting it upwards by a factor of A. So they just need to fit it like that. So here's what the graph looks like, but you want to turn this into that. And your calculator will do that for you. See what they want here. Yeah, they give us data. I don't know where the table is here. Here we go. So if you have like data, so what we have here is we have years and the interest rates. So what we could look at is the doubling time. Like in 1950, how long would it take to double your money? In 1960, how long would it take to double your money? It's a different time because it's a different interest rate, right? So if you graph this, right, let's see, like I said, this is, if you're compounding only once a year, this is your doubling time. Time to double your money is this. It's a function of R. So you're just plugging in these different R's and graphing. Actually, you're plugging in different times here. The other graph, where's the graph? You got a different time, a different rate. Just plot those points. Enter the data into a graphing calculator. Find the logarithmic regression equation. So I guess there's a menu. There it is. You can find it. You want a plus b natural log of x. The data set in the regression equation are graphed. Using trace, we predicted the home ownership rate in 2025. So once you plugged in this data, hit the regression button, and it's made a function that fits this data. Then you could just, the trace button just allows you to like pick a point and drag it around on the line. So you can drag it to 2025 and look at the output. And let's see, in example 11, we let x equals 0 represent 1900. If we let x equals 0, 1940, we would get a different equation. We would not let x equals 0 represent 1950, the first year in table 1 or any later years, because you can't plug 0 into a log. Yeah, so be careful as to what you call time 0, right? You can't plug 0 into a log, so you want to choose your starting time wisely. That's it for 2.6. All right, so now that we're done with 2.6, we need to change the due date for 2.6 to a week from today. How are y'all doing on catching up on your homework? You only have to do like 2 sections of homework a day, right? Every day. What one from last week is due on the 6th. Hold on. Well, one of them was due on Tuesday. The one we finished due on Tuesday is due today, homework 17. And yeah, the one that we finished on Thursday is due Thursday. Now the one we finished today, let's see. How do I do this? Change dates. There we go. 2.6. All right, so 2.6 is due. What is today? The 4th? So a week from today is the 11th. Yeah. Let me see. Let me check and make sure, because half the time when I click on this, it doesn't do it. Yeah, it's been changed. So a week from today, 2.6 is due. And we're basically out of time. So let's do an exam. Daily exam number 21. One of these. Solve for x. Solve for x. Let's pick one out of the book here. these two. And I'm gonna do the same thing. Give you kind of an easy one. I'll give you one that has more terms where you have to use your properties blocks, combine them and stuff. Yeah, these are the ones I want. Change number one. Oh, it's too easy. Do this one. X, this one's easy because the X is already right there, right? And let's do one where the X's are a couple of different X's. There. So this X is already on one side of the equation by itself. You just need to combine these logs and then do b to the power of both sides. This one, you got to get you have to combine the logs to get the X's together. You should be able to do about 5 minutes. If you know what you're doing, you can do them in just a few seconds. If you need help, use the tutoring lab. I think you can zoom in over there. Take advantage of your resources here. And that's it for today.